Good evening, Chemistry 20s. Today's gas law we're going to focus on is called Charles' law. If we take a look at Charles' law is a relationship between the temperature of a gas and the volume of a gas. Again, we're going to concentrate on the fact that this is true only when the quantity of gas, the amount of gas is constant, as well as the pressure of the gas is constant. In order for us to talk about this relationship between volume and temperature, we need to understand temperature first. Temperature in the lab, we measure in degrees Celsius. However, to use Charles' law, we cannot use degrees Celsius. Every temperature we have has to be converted to a unit called Kelvin. And to convert from Celsius to Kelvin, what you do is you add 273.15 to your degrees Celsius value. Now, like in atmospheres and millimeters of mercury and kilopascals, when we had to memorize that conversion, in temperature, you also have to memorize that to change from degrees Celsius to Kelvins, you add 273.15. So what I would like us to do is I'm going to do the first one with you. And so, I went back a page. So 25 degrees Celsius, we are going to add 273.15, and we're going to get the value in kelvins of 298.15 kelvins, and it's a capital K. 37.8 degrees Celsius, we're going to add 273.15. So again, the value is going to work out to be 310.95 kelvins. And minus 15.4 degrees Celsius, we will add 273.15, and the value will be 257.75 kelvins. Now, sometimes the question is going to ask us for the answer at the end to give us the answer in degrees Celsius. We still have to use the formula in kelvins because that's how the formula works. Always has to use kelvins. However, to get out of kelvins, you're going to now subtract 273.15. So we're going to take our Kelvin number, subtract 273.15, and this is going to represent 0 degrees Celsius. 251.35 minus 273.15 is going to get us negative 21.8 degrees Celsius. And the last one, minus 273.15, is going to get us 45.1 degrees Celsius. So to get into Kelvin, you add 273.15. To get out of Kelvin, you subtract 273.15. Okay, looking at temperature for a second. Remember, temperature is going to be almost, if you want to think of it as a measure of how fast the particles are moving. So if it's hot, those particles are going to be moving very, very fast. If it's slow, those particles are going to still be moving, but they're going to be moving much, much slower. So when we look at temperature, I want us to think about it as a measurement in kelvins. We're looking at kelvins, not the Celsius system, not degrees Celsius. We use this system because originally 0 on the Kelvin scale is actually called absolute 0. And that's where particles don't move at all anymore. So, like we did with Boyle's law, let's look at this comparison when we go to graph it. Okay, Boyle's law was something called inversely proportional. When pressure went up, volume went down, or vice versa. This is not true for Charles' law. In Charles' law, volume and temperature have a direct relationship, meaning when volume goes up, temperature is also going to go up. Or when volume goes down, temperature is also going to go down. This is called directly proportional or a direct relationship. Now, if I look at this a little closer, I think this makes sense. So again, for us to study Charles' law, we still have two assumptions. First assumption, pressure in this relationship is going to stay the same. It's going to stay constant. The second one is number of gas particles is going to stay constant. So if I take a look at this scenario here, I think there's 12 dots. Those are 12 gas particles. In the second scenario, it's still 12 gas particles. The gas particles are not going to change. We're going to have still the same number of moles. Notice the difference between these two scenarios is temperature is going to go up from 15 degrees Celsius to 30 degrees Celsius. Temperature is going up. When temperature goes up, volume means the distance between the particles is also going to increase. So because the temperature is going up, the particles are moving faster, it's going to cause my device, whatever it is, a car tire, a balloon, whatnot, to expand a little bit. That's going to leave more room between the particles. And volume is distance between particles. So as temperature increases, you'll notice the spacing between these particles as we go from scenario 1 to scenario 2 also increases. This is what directly proportional means. Now, here is our formula. So I'm going to go to my pen pointer tool for a second. So in my formula, it's still ones and twos, meaning initials and finals. However, Charles' law is V1 over T1 equals V2 over T2, where V1 represents the initial volume, T1 represents the initial temperature, V2 represents the final volume, and T2 represents the final temperature. Now, I want to look at the units for a second. Whatever the unit is for volume, they've got to be the same. So milliliters, milliliters, liters, liters. We don't care what the unit is for volume as long as they are the same for initial and final. For temperature, this is the one that matters to us. And this is worth a star or a highlight or something. Temperature, when doing Charles' law, must be in kelvins. Therefore, you have to convert your degrees Celsius to kelvins in order to do the question. When we're in the lab, we're still going to use a thermometer. We're still going to get our values in degrees Celsius. That's our device. That's our measuring device. However, when we go to do the calculation, now you have to convert. Again, our assumption is the number of particles or the amount of gas is held constant, and the pressure of our gas is also held constant. You saw a slide very similar to this when we did Boyle's law. Again, I'm going to reference you to page 3 in your data booklet. By now, you have either noticed that you do have STP and SATP conditions on page 3, or you have already gone ahead and you've already put this table on here. Yesterday, for Boyle's law, we needed the pressure at STP and the pressure for SATP. Today, for Charles' law, you will need the temperature at STP, which you will notice is 0 degrees Celsius, and the temperature at SATP, which you will also notice is roughly room temperature, 25 degrees Celsius, or 273.15 kelvins, and respectfully, 298.15 kelvins. Please make sure these are in your data booklet, ready to go. Okay, let's try 2 examples. So, example number 1. We have an initial volume of 30.2 liters of gas in a container is heated from, so T1, negative 33.15 degrees Celsius, to T2, 25.00 degrees Celsius. We want to know what will the volume V2 of the new container be. Now, the first thing we're going to do, and why I always do all this work on the left is, this is where we're going to change units. We are not happy with degrees Celsius. This formula needs to be in kelvins. So we're going to add 273.15 to each of these temperatures. So T1, when we add 273.15, is going to be 240 kelvins. And T2, when we add 273.15, is going to be 298.15 kelvins. This is where I want to do the conversion of units. So now we're happy. Kelvins, kelvins, liters, my answer is going to come out in liters. So as always, 1 mark for the formula. V1 over T1 equals V2 over T2. So we are going to solve for V2, which means I got to get rid of T2 since it's in the basement. We're going to move it upstairs. V2 equals V1 times T2 over T1. And let's substitute in our numbers. 30.2 liters times 298.15 kelvins divided by 240 kelvins. So when we go to type this in the calculator, 30.2 times 298.15, enter, divided by 240. And my answer in the calculator is going to be 37.51720.833. And of course, Kelvins cancel, so my units in liters. I go back to the original question, 4 sig digs, 4 sig digs, 3 sig digs. So I look, this isn't going to have any effect. So my answer is going to be 37.5 liters. Now, ask yourself, does the number make sense? My temperature went from negative 33 degrees Celsius to 25. My temperature went up. Therefore, I expect my volume to go up. So 30.2 goes to 37.5. We can assume I did the question correctly. 1 mark for formulas, 1 mark for substitution with unit, 1 mark for answer with units and correct significant digits. I would like you to try this question and pause the video, go back and check your work when you're ready to check over your answer with me. So I have V1 equals 2.10 liters. T1 equals 15 degrees Celsius. V2 equals 561 milliliters. And T2 is what I'm trying to find. So first thing I have to do is convert by adding 273.15. Got to get my temperatures to kelvins. So that's going to be 288.15 kelvins. I also don't like having milliliters and liters, so you can change either one. I like going from liters to milliliters better, so I'm going to multiply by 1,000. So 2,100 milliliters. You get 1 mark for your formula. V1 over T1 equals V2 over T2. I'm going to solve for T2. I will not solve for a variable in the denominator, so the first thing I'm going to do is move it up. If I move T2 up, I want to move V1 down, so they're going to exchange places. If T2 comes up, I want to also move T1 to the other side. So I'm going to have T2 equals T1 times V2 over V1. And we're going to substitute our numbers in. T1 is 288.15 kelvins times 561.00 milliliters divided by 2,100 milliliters. So T2 is going to equal, multiply the two numbers, divide by 2,100. We're going to get, and again, you're only allowed 3 significant digits, 77.0 kelvins. Now, the question says, what is my answer in degrees Celsius? So you get 1 mark for the formulas, 1 mark for substitution. You have to give me your kelvins in significant digits, okay? But on your calculator, leave the full calculator number. Now subtract 273.15 and get me the temperature again in the correct number of significant digits. So when I subtract 273.15 from 77, I'm going to get negative 196 degrees Celsius. you will get 4 marks for this question because there's an additional mark for the second answer.